here. We've been talking about chapter 13, I believe. We've been talking about equilibrium, and we've been focusing on last couple times here, really solving equilibrium problems. And again, pretty much in a lot of cases in this class, you can't go wrong with an equilibrium type situation to solve it with an ice table. So, if you're thinking about what I should do, that's a pretty good idea as to what you should actually do. Again, the I is the initial, the C is the change, and the E is the equilibrium in this case. Really what we're doing when we do an ice table is it's really the change is what we're looking for, and that's usually represented by an X. Also important in the change part of it, like we talked about, that you do take the coefficients into account so that you have the right mole to mole relationship. Now, there's a few different ways we could kind of solve it. We saw a couple so far. Again, you could use the quadratic. And again, that quadratic is something like ax squared plus bx plus c equals 0, where x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Again, as we talked about, that will give you basically two x values. And really only one of them will make sense. And when we talk about it sort of making sense, remember that that x value that you get is basically your equilibrium line here. So whatever it may be, it's all those x's that we see in the equilibrium line. So one of those values of x will lead you in most cases to a negative sort of concentration or a negative pressure, which you cannot have. That would mean obviously the other value should be the correct value. Now, remember that you can get pretty much any combination of x values. It could be two positives, two negatives, a positive and a negative value. So you really do want to check it. For example, the one maybe if you did the quadratic last time, you would get an x too big. So you do want to make sure you check and not just go, okay, there's a positive number is probably okay. You got to check both numbers, but one of them will get you that sort of maybe value that will be negative. The other way is that we finished last time, we did have sort of a perfect square situation on both sides, and you can sort of shortcut some of those calculations. As I posted online, you could have also done the other one through the quadratic formula, and you do get the same answer. Again, in that case, you did get one that was too large to use, and the other one was the one that we got when we did the square root basically of both sides. We also talked about, I think, Q as well last time, perhaps. Q, again, is the reaction quotient, and that is calculated the same as K. So you basically do the exact same thing. So Q is your products over your reactants, also obviously with your coefficients as well. And we could use, again, Q and compare it to K to decide if we're at equilibrium. Either it'll be too big, or Q would equal K, or Q would be less than K. And in this case, you're not at equilibrium, and to reach equilibrium, you would need to make some reactants in that case and some products in that case. If you do calculate Q and it does equal equilibrium, or the equilibrium constant, it is at equilibrium, so obviously you would be done. You always want to calculate Q in kind of two situations. One, again, as we talked about, it's just a straight up sort of Q type question where it basically asks you that, are you at equilibrium, and which way you need to go to reach equilibrium if you're not. The second is anytime, again, that you pretty much are given the starting amounts of everybody in the reaction, you should calculate it to make sure that you're not at equilibrium, and also make sure that you don't have to kind of switch around your negatives and positives there on the change part of it. Any questions on any of that stuff we talked about last time? All right, so let us do a fun one here. No, probably not. Let's do it. What is the equilibrium concentrations of everybody here? In this case, we're going to start with 0.00623 molar H2, 0.00414 molar I2, and 0.022 molar HI. The equilibrium constant is 54.3. So take some time here and work it out. I will as well, see if I remember how. Okay, let's take a look and see how we're doing on this one. So here we're given the initial concentrations of pretty much everybody that's there. So we got H2, I2, and HI. So we actually have the concentrations to start with of each of these. So this is really a situation where you would actually want to calculate Q here just to make sure everything is what you would think. If we didn't do that, maybe you'll be okay. Let's see. So Q is again calculated the same as RK, which would mean it'd be the concentration of HI, and we would square it divided by the concentration of H2 times concentration of I2 in this case. And again, we could do this because we are given the initial amounts of each of these. So we should check 0.00623 and 0.00414 in this case. So if we do that here, we got 0.0224 squared divided by 0.00623 and divided by 0.00414 gives us a 19.5 in terms of our Q. So in this case, Q in terms of K, our K is 54.3, so Q is less than K here. So it does tell us that we're not at equilibrium, which we probably knew to begin with because it wouldn't be much of a problem if we were at equilibrium. But more importantly, we know to reach equilibrium, we do need to make more products, right? So what that helps us is with the change part, we can feel confident that the minuses should be on the reactant side and the positives there should still be on the product side. Again, if it was opposite of this, the thing that would change is the reactants would be positive and the products would be negative if we had to go in the other direction to reach equilibrium. So you should calculate it here in this case because you have everything. If you blew by that and did not do it, you're actually okay. You got lucky here in this case, and you're which should be still okay. All right, so we do want to obviously do an ice table here. So I'm going to flip the page there and rewrite the equation. So we've got H2 plus our I2 going to our 2HI and our K value here being 54.3. So initially here we have 0.00623, 0.00414, and we do again have an initial concentration here of our product in this side. Now that we calculated Q, we can feel confident that it is heading to the product side. So we know that when we do our change here, this should be minus X, this should be minus X, and don't forget that this will be plus 2X here. Again, a couple common mistakes forgetting the coefficient. And sometimes people will put minus there because they're used to like a number minus something instead of plus. So it should be plus in that case. Coming down here, going to bring everybody down, and we're going to get 0.00623 minus X, 0.00414 minus X, and 0.0224. Once again, that is plus 2X in this case. This is going to go into our equilibrium expression, which is our products, which is our HI squared divided by our H2 and our I2. And in this case, this will equal our 54.3. Any questions on the ice table here? Okay, so we are then obviously going to put that into our expression here and get really sad because it looks like a lot of math coming our way here. So this is 2x squared. That's going to be 0.00623 minus x, 0.00414 minus x. And once again, that's going to give us 54.3. All right, so we got obviously some factoring and all that good stuff to do. So I'm just going to kind of break it apart and kind of do them separate and then put everybody back together here. So I'm going to do the top part first on the left. So the top part would basically be 0.0224 plus 2x times 0.0224 plus 2x. Once again, we're going to go in and out right as we do that for both of these guys here. And if we do that, we will get for the top guy there 0.000502 plus 0.0448x plus one more is 0.0448x and a 4x squared. Combining our x terms here will get us something like 0.000502 plus 0.0896x plus 4x squared. So that basically is the top part there that we need. We're also going to do kind of the same thing here for the bottom part. So I'll do that in this color here. So if we did our bottom here, that's going to be our 0.00623 minus x, our 0.00414 minus x. Once again, here we're going to go in and out, and obviously in and out as well. So doing that on the bottom part there, somewhere there it is, will give us 2.58 times 10 to the minus 5. Then we will have minus 0.00623x minus 0.00414x, and then we will have a plus x squared. Combining once again our x terms there will give us a 2.58 times 10 to the minus 5 minus 0.01037x plus x squared. Any questions on any of that? So now I got my top part, I got my bottom part, and we'll put it back together here for just a second. And if we do that, we will have, we'll go here. Up on top actually will be this guy, so I'll just leave it there. And then on the bottom here, we'll have our 2.58 times 10 to the minus 5 minus 0.01037x plus x squared, and that will equal our 54.3. Just kind of borrowing that, so let's rewrite it there. All right. Steal that right there. All right, at this point, what we need to do is take the bottom, everything here on the bottom, and we're going to multiply it to the other side. I'm clearly out of room, so I'm going to flip the page there and continue up there. So if I do that, that will get me here. Multiplying that bottom to the other side. On the left-hand side, it hasn't changed, so we still have 0.0, or the top, I guess, on the left, 0.00502 plus 0.0896x plus 4x squared. Now taking the bottom there and multiplying it to the other side gets us 54.3x squared minus 0.5631x plus 0.001401. At this point, I'm going to bring everybody on the left-hand side to the right. That way my x squared is positive. It doesn't matter, but I'm just going to kind of do that. So I'm going to bring everybody here and either subtract or obviously add it to the other side. When I do that, that finally gives me something here to work with, which is 50.3x squared minus 0.6527x plus 0.000899 equals 0. Questions up to there? All right, so that is our A here, our B with the negative, and our C. So going into our quadratic, that's going to give us x is equal to 0.6527 plus or minus the square root here. So if you do everything inside the square root and get a number, that is 0.2451389. After you take the square root of that guy inside, you end up with 0.4951. That's going to all be divided by 2 times 50.3, which is 100.6. This is going to give us our 2x values, our positive way, and then subtracting. And that will give us an x value of 0.01141, or doing the subtraction way, 0.00157. Any questions so far on that there? Yeah. I didn't divide, I basically subtracted it over to combine the terms. So basically 54.3 minus 4x, yeah, and then minus 0.5631 minus 0.0896, and then 0.001401 minus 0.00502. So basically on this case, everything on the left-hand side gets subtracted to everything to the right-hand side to combine them. Other questions? Okay, so looking at our ICE table as a guide here, and what I'm going to do is just write the equilibrium part of our ICE table. Our equilibrium part of our ICE table, we have H2, I2. I guess that was a good choice there, 2HI. So on the equilibrium part, we got 0.00623 minus X. We got 0.00414 minus X. And for our 2I HI there, we got 0.0224 plus 2X. Make that a little bit better there here. So this is for, obviously, from our ICE table here. This would be H2, I2, and 2HI. All right, so if we look at our equilibrium line at that point, we should hopefully see that this number right here, when we put it back into either here or even here, will give us a negative number. So that's a little bit too big to use. So this would be not so good, too big. That should mean that this guy here should be our correct X value. And now we're ready to hit everybody's equilibrium. So with our H2, it will be 0.00623 minus X, which is 0.00157. Oh, that rain's coming down good out there. Jeez. 0.00623 minus 0.00157 gets us something like 0.00466, and this is molarity there for our H2. For our I2, it will be 0.00414 minus X. Going to get us 0.00257 molar. And lastly here, our HI is going to be, remember that we do have an initial concentration that goes with that guy. So 0.0224 plus 2 times X. 0.0224 plus 2 times 0.00157 here. 0.0255 molar in this case, yeah. And once again, we could check it really quick, and it should be hopefully 54, because I don't want us to go back and fix anything. Hopefully 0.00466 divided by 0.00257, and you got about 54.5, which is pretty close with rounding to where we were at. Yes. Any questions on any of those steps there? So once again, here you can use quadratic, and it will give you, in this case, 2 positive numbers. You do have to check that equilibrium line. One of them really should lead you to a negative number, which is the one you should throw out, and you should keep the one that does not give you that. At least there's no leaks, right? That's good. We're on the ground floor. It's leaking on the people on the top floor, probably. All right, any questions on that one there? Yes. You you should. So that's when we're talking about Qs. Really, the second place where you should use Q is whenever they give you in a problem like this, like an equilibrium problem, the initial concentrations of everybody. Um, the odds are it's not at equilibrium. Otherwise, like it wouldn't be a very good problem. But what it really helps you when you do the Q part is once again that you can feel confident in this part of it here where you're doing your change. And if we'd happened to come out the other way where, Q was say greater than K, that would mean that we would need to have made reactants in this case to reach equilibrium. And what would have happened is instead of our reactants here being negatives or subtracted guys here, they would actually be positive. So they would switch there and you would solve the problem differently. You would have plus X and plus X on the left and minus 2X on the right. So that's really the purpose why you would want to do Q in a situation like this. In this case, it confirmed our probably basic idea of it's going to the products, but it could have actually went the other way. And if you did happen to go the other way, where the positives were on the reactants and the products there was negative, you could use the same K value as it's written, just do it that way. You could also reverse the reaction, but if you did reverse the reaction, you have to reverse the K, inverse the K as well. So there's two ways you could solve it. You could leave it like it is and just solve it with the negatives and positives on the correct side, or you could reverse the reaction, but then you have to actually change the K value if you do that. Other questions? Yeah. Did I check if the Q, is that what you're asking? Yeah. Yeah, it was what we did here at the very beginning. So because we were given the initial concentration, everybody, you have enough information to go directly into Q, and Q is calculated the exact same way as you calculate K. So it's products over reactants using the coefficients as the exponents. So basically that's what we did here. We basically just threw in our initial concentrations into the Q expression, and then we basically compared it to the K value that was given to us. And it wasn't equal, which tells us first off, it's not at equilibrium. But in this particular case, it was less than, which confirmed to us that it has to proceed to the product side. And that's what gives us the change part of this important. It keeps, we know for sure it's going to be negative on the reactants and positive on the products. Other questions on that? Okay, fun with math continues here. Here we go. All right, let's try another one here. If the Kp for this guy is 4.31 times 10 to the minus 4, calculate the equilibrium pressures of everybody. If we started with 0.862 atmospheres, 0.373 atmospheres of H2 in a volume of vessel. So again, even though this is pressures and you have a Kp value, it works the same way. So you just put the pressures into the ice table and proceed that way. Again, remember that it does need to be in atmospheres, which obviously it is in this case. So you should be good, hopefully. All right, so give it a try, see what you come up with there. Okay, let's take a look at this particular one here. So we have the Kp given to us. We have some initial pressures, and we're looking for the pressures of everybody at equilibrium. As I mentioned earlier, it's really worked the same way as any other ice table. If you're dealing with pressures, obviously you have a Kp value. And again, this is definitely the place where you want to make sure that the pressures are in atmospheres before you go into the ice table. And once again, even if the question asks for the answer in some other unit of pressure and they give it to you in some other unit of pressure, it does need to be in atmospheres when it goes into the ice table. We will write our equilibrium expression here, which would be, in this case, the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure cubed of H2. And again, this will equal R 4.31 times 10 to the minus 4 in this particular case. We're going to rewrite our ice table plus H2 and our NH3 here, like a 2 there. And 0.862, 0.373. 373, and lastly here 4.31 to the minus 4. Okay, so got all of my numbers there. All right, so we'll do our ice table. That's our initial pressures in this case, and we'll have 0 here for our NH3. At this case, we can assume that it's going to our product size since we were not given anything involving our products here. So our change will be minus x, it will be minus 3x, again for the coefficient, and we also got a plus 2x happening there. That's going to give us, when we carry down everybody, 0.862 minus x, 0.373 minus 3x, and 2x in this case. Any questions on that there? Like normal here, we're going to put this into our equilibrium expression. So that is going to give us 2x squared up on top, divided by 0.862 minus x times 0.373 minus 3x. And we got to remember we still need to cube it. And that will equal our 4.31 times 10 to the minus 4. At this point, we have some really scary looking math, right? So we clearly should just like go to the next problem would probably be the right choice here and just forget about this one and hope it doesn't come back. But in case we should do this, we definitely don't want to do the scary math or anything like that. So what we have in this situation is a couple things we want to think about. So first off, when we look at this K value here, is this a large value of K or a small value of K? It is a small value of K. And because it's a small value of K, that means when we reach equilibrium, should we mainly have reactants or products? Yeah, so since we have a small value of K, we mainly should have reactants when we reach equilibrium. And that means, will the change part be a lot or not very much? We would expect the change here to be relatively small. So in a situation like this, where you do have a K value that is small, and remember, pretty much anything that's small is considered less than 1, basically, you can make the assumption, and you could assume that because the change is not going to be all that much, that x is going to equal 0. Now, clearly, we cannot get rid of all the x's, otherwise we have nothing to solve for. So the x's that we're talking about in this situation when we make this assumption are pretty much any x's you're going to subtract from a number or add to a number. Those are pretty much the x's that you're going to get rid of. The reason we can't get rid of this x here is 0, right? So if you started at nothing, even if you made a little of something, that's more than you started with. So it's sort of a significant change, right, for our products in this case, because basically we started with nothing. So whatever you got was pretty significant. In terms of our reactants, because we're actually starting with something there, the change is going to be relatively small. So that's going to make this math here hopefully a little bit more manageable. So if we assume that x is equal to 0, that will give us our basically 2x squared divided by 0.862 times 0.373. Once again, we still need to cube that number, and that equals 4.31 times 10 to the minus 4. That looks a lot better to try to solve than the previous one. So here we're going to multiply these guys together. And that's going to give us 0.373 cubed times 0.862. That gets us something like 0.04473. We're then going to multiply that number to the other side. And when we do that, that will give us 4x squared equals 0.00001928. We're going to divide by 4, and I'm also going to take the square root after I divide by 4. So I'm going to divide by 4 and do a little square root action on it. And if you do that, Gets you an X value of 0.00220, we'll call it in this case. First off, any questions on that map there? Now, because we made the assumption, and whenever you make the assumption in this situation, you do need to check it. So you do need to check your assumption to make sure that it's okay. And the rule that we're going to follow in here in terms of how we check our assumption is we're going to follow what's sometimes referred to as the 5% rule. So the 5% rule is pretty simple. You take the X value that you just got. So we will take our 0.00220 and we divide it by whatever we were going to subtract it from. So in this case, basically the initial concentrations. So we're going to take 0.862 times it by 100%. And if we do that, 0.00220 divided by 0.862 times 100 is about 0.255%. That is less than 5%, which means that is good. In my experience, if you check one and it's good, you're probably good on both, but you could check them both if you want to. You don't need to. But for example, if we did the other one, we could even multiply it by 3. So 3 times X divided by the initial concentration times 100%. And if you did that guy there, 3 times 0.00220 divided by 0.373 times it by 100 gets you about 1.77%, which is also still less than 5%. So again, you should definitely check one. You don't really need to check them all. Usually, again, if that one's good, the other one should be good. Now, let's say it was above 5% or above. What that means is you would need to go back and solve it some other way. And for us, that would probably mean you need to go back and do the quadratic formula, basically, in that situation. Or just skip the problem, whichever one you like better. I don't know, whichever one you want to do better. All right, so now that we checked it, it's all good. That means that we will use this X value for everybody there in the table, and we could get our pressures. So the partial pressure here of N2 should be 0.862 minus our X, 0.00220. And that gets us 0.862 minus 0.00220. We'll go with a 0.860 on a round there. This should be atmosphere since these are pressures. The partial pressure there of H2 would be 0.373 minus 3 times our X, 0.00220. And that gets us 0.366 is good. Atmospheres. And lastly, here our NH3 would be 2 times X, 0.00220. Gets us 0.00440 atmospheres in this case. Question on that there. Yeah. We assume X equals 0 in this case because it is the K value that we have there. It's a small K value. And what that means is when it reaches equilibrium, we mainly should have reactants present, which means because we mainly should have reactants present, this change part here should be a relatively small amount and almost negligible, the amount that's going to happen, the change. And that means that we can make that assumption, and we do have to check it. And it's okay as long as basically that change is less than 5% of what we started with, and then you're okay in that case. Yeah. Yeah, you could try it in any situation where you have a small K value. but you should definitely check it because there will be lots of situations or a number of situations. I won't say lots, but there'll be situations where it will not be good. It will be too large of a change and stuff like that. You'll need to go back and solve it some other way. So you shouldn't just blindly use it without checking it, because you might be surprised that it's not more than 5% and stuff like that. So you definitely want to make sure you check it. Why could I not have done the assumption on the previous 3 equilibrium problems we did? Yeah, so if you look back on the 3 that we did previous to this, I think our first K value was 7. The last 2 were like 54.3. So those are relatively large values of K, which means the change is going to be pretty significant going to the product side. So we cannot use it in a situation like that. You could only use it really in this situation. Any questions? Yeah. Yeah. Because that's technically what we were subtracting the change from, is that 3 times X. So that's why I put the 3 there. We happen to have actually a number there. A lot of times it'll just be minus X on that side or something like that. So you don't have to worry about it, but you could actually multiply the X value by 3 in this case and also divide it, and you're still okay. Other questions? Okay, so we've seen a number of ways that you could solve these sort of ice table type problems, equilibrium problems. You should do an ice table in an equilibrium situation like this. You can obviously use the quadratic. We saw a situation where you had a perfect square, or you could use the quadratic if you wanted to, or here you could do the assumption as well. In retrospect as well, if you probably wouldn't maybe want to do it on this particular one, but you could do the quadratic instead of the assumption as well. And again, it should come out about the same, depending on, you know, or a little bit of rounding and stuff like that. So you do have options. So this is pretty much the way that you'll solve these type of problems. The only other way that sometimes people will solve these problems, and I might have mentioned it earlier, is through a process known as successive approximation. And we will not be doing it that way here. What successive approximation means is you basically choose an X value because you know it should be smaller than, say, this number, and you put it in there and you solve for X. So you would put that X value in here and here, and then solve for X. And you would continuously kind of put numbers in until the number you put in and the number you get out are the same, which if you choose really badly could be a very long night for you trying to do those type of problems in that way. So yeah, so that's successive approximation. You basically put the X values in for everything but the top guy, and then you solve for X. And if they don't equal each other, whatever X you got, you put it back in and do the same thing until you put it in and what you get out are the same. So we will not do successive approximation in here. The toughest it will be the quadratic, but in case in some books and stuff like that, people still sort of do that successive approximation, and that's the idea behind that. Any questions on how to solve these problems here? This is definitely the calculation of the season, yes? So this is stuff that you need to do. We're going to do some twists and a little changes to some of this, but the core calculation is these ice tables. Yeah. Any questions on these? All right, so the next thing we're going to talk about then is to finish up is what's known as Le Chatelier's principle. And the idea behind Le Chatelier's principle is a pretty sort of simple idea. You basically have a system that's at equilibrium. And then frankly, you do something to it that messes up the equilibrium. So you add what is sometimes referred to as a stress. You add a stress to the system. And basically what's going to happen when you add the stress is it's going to mess up the equilibrium, which means at that point, the rate of the forward reaction and the rate of the reverse reaction will not equal each other. But because it is an equilibrium type reaction or a reversible reaction, the reaction itself is going to want it to once again reach equilibrium. So for it to reach equilibrium, there's usually 3 things that might occur. It will want to come back to equilibrium. And it's going to come back to equilibrium by sometimes referred to as shifting to the right. And when it shifts to the right, that means that we're going to make more products. It may shift to the left. And in that case, we would make more reactants. And there are certain things that may occur to a system that will frankly cause no change. So those are kind of your three options when you're dealing with Le Chatelier's principle. Either whatever you did to it will cause the reaction to shift to the right to make more products to once again reach equilibrium, or it will cause it to shift to the left to make more reactives to once again reach equilibrium, or frankly, nothing will happen basically as a result of it. So when we talk about stresses, there are several stresses that could happen. Stress could involve concentration. So either you add more or you remove. It could deal with volume and pressure. It could also deal with temperature. Either obviously raise or lower the temperature. Or lastly, a stress can be a catalyst, which as we talked about, again, is not a reactant, not a product, but just there to sort of speed up the reaction. So each of these can cause sort of different things to occur, different changes to occur, depending on whether you are adding or removing concentration, changing the volume or the pressure, and if you're playing with the temperature. So let's talk about each of these here and sort of see, how its effects on the reaction and what occurs. So we're going to start with concentration, I think. Actually, I'm just going to back it up here and use some of these pages, I think. There we go. Let's start with concentration. So obviously, as I mentioned, there's pretty much two things you could do. You could either add more. And whenever we add more concentration, it will always shift away from where you added it to. So if you add reactants, it will shift to the products. If you add products, it will shift to the reactant side. The other thing that you could do is remove. And when we remove, it will always shift towards the side you removed from. So AA is a good way to remember add away. And when you remove something, it comes towards it. So let's take a look at sort of what's happening. So if we take, let's see here, a little award-winning stick figures. The advanced stick figures, they have faces. There we go. We'll see on the left-hand side here, this is the reactant side, and on the right-hand side there, that is the product side. So we're at equilibrium here, in this case. Equilibrium position number one. Now let's say somebody decides, hey, that looks like fun. I'm going to hop on over here. When somebody hops on the right-hand side, this is the situation that will then develop. So good in this case. We have clearly messed up the equilibrium, right? To fix the situation, do we need more people on the left-hand side or the right-hand side? Yeah, so we added people to the right. In this case, to fix it, we would need to shift away from the side that we added it to. And once again here, we will now return back to equilibrium. Oh, I should put them back on there, I suppose. And now we are back to equilibrium at that point. So we added more products in this example. In order to fix that, we actually had to make more reactants. In this particular case, when we add more products, what we're essentially doing is kicking off which reaction, the forward reaction or the reverse reaction? we are kicking off the reverse reaction because we have a lot more products. So those guys are going to start reacting more, and that's going to cause more reactants to basically be made. Now, let's say we took the same situation here, and we had our system here at equilibrium. This guy will be our reactant. This guy will be our product, and we're at equilibrium again. And this guy decides, well, I had fun. I'm going to get off. And when this guy gets off, what's going to happen in this situation is this still. We obviously have messed up the equilibrium. In order to fix this, we need to put more people on the left or more people on the right. We need to put more people on the right-hand side, right, where we removed it from. The result of that is we will once again come back to equilibrium in this case. So what happens when we basically get rid of a product? You could think of it like it made a hole over there, right? There's less products now. Now there's more reactants, which means that's going to kick off the forward direction in this case, heading towards the product side. And that's going to cause, if you want to think about it, like filling the hole with more products to bring it back up to where we lost it. Question on that there. So it's pretty simple to add more of something, right? So we could add more of something by just taking it off the shelf, right? And dumping it into your test tube, your beaker, whatever you may be doing this in. How do I remove something that's in like a solution? Do I reach in and grab it out, whatever's in there with my hand? That seems not such a great idea. Safety video would probably tell you not to do that, I imagine, right? So how do I remove something from a solution? Not necessarily evaporation. Any ideas? What else we could maybe do? So basically, if I have a solution, I basically have ions in there, right? They're floating around in there, positive, negative guys. That's really what a solution is, right? It's basically ions floating around. I could add something to it that will maybe react with one of these ions and bring it down as a solid precipitate. So I could add something to it. I can make a precipitate. And essentially what that's doing is grabbing out the ions, right, from solution. And that's effectively removing it. And we know that solids are not included in the equilibrium expression. So that would be like reaching in and taking it out. So one way that you can basically remove something is to add something to the reaction that will react with maybe a reactant, maybe a product, and will form a solid, and that will essentially be like removing it from that equilibrium. Another way is something that's maybe a little less visual that you might not be able to actually see that you did. Obviously, in a solid, you could clearly see you made a solid. And that is if you have a beaker that's floating around and maybe there's hydroxide ions in it, maybe there's H+ ions floating around. You could either add an acid or a base to that solution. And let's just say, for example, we had hydroxide ions floating around and I added an acid, which is H+. H+ and OH- will make water, yes. And water is not part of the equilibrium, right? Because it's a pure liquid, but it's essentially, in this case, removing hydroxide ions from solution. Or again, if you had H+ in solution, you could actually add a base and it will remove the H+ from the solution. So the formation of water is another very common way that you could actually remove something from a solution. You would probably maybe visually not be able to see that you made water, but it would be like removing those guys. Any questions on that there? Okay, so concentration here. Let's then talk about another topic of that, which is pressure and volume. And usually when we talk about pressure, we're talking about gases in this case. And they are related to each other. Perhaps you remember a guy named Boyle. He had a law, right? When the pressure goes up, what happens to the volume? volume goes down, right? They're opposites of each other, and vice versa. Pressure goes down, volume goes up. So you can kind of think of that sort of relationship here when you're dealing in a reaction that involves pressure and volume. If the pressure goes up because the volume went down, so basically here the pressure went up is the change that's occurring. We kind of want to bring the pressure back down. So that's the opposite of what sort of happened in this situation. Would I need more or less gas molecules to bring the pressure kind of like back down? I would need less gas molecules, yeah? So in this case, because the pressure kind of went up, to bring it kind of back down, we would need less gas molecules. So it would shift to the side with the least number of gas molecules. And that obviously is dependent on the reaction you're looking at. That may be the reactant side, maybe the product side. Opposite is true here. If pressure goes down, the volume went up. In this case, because pressure kind of went down, we want to bring it back up. We would need more gas molecules to fill it. So it would shift to the side with more gas molecules. I personally think about it in terms of volume. So small volume, less gas molecules, larger volume, more gas molecules. So that's a good way to sort of remember it. So let's just say, for example, we had let's say in this reaction here, we added more D, we removed A, we increased the volume, we increased the pressure, and we added more C. All right, so in this one, for each of those situations, will it shift to the right? Will it shift to the left? Should shift to the left away. Adding more D basically would promote the reverse reaction to occur, which is why it will go in that direction. If I remove A, which is over here, it should head up to the left as well. Again, it's like a hole on this side, which means really you have more product, so also will cause that reverse reaction to occur. If I increase the volume, which way? It should go to the right. When I increase the volume, that means the pressure comes down. To increase the pressure back up, and then a bigger volume, I need more gas molecules. Left-hand side has 3 gas molecules. Right-hand side has 4 gas molecules, so it would shift to the right. Increasing the pressure here means that actually the volume gets smaller. So in a smaller volume, we would want to shift it to. So that would be to the left. And lastly here, if we added more C, that would cause it to shift away from it, which would be to shift to the right. Again, more C would actually initiate the forward direction of this reaction to take place, which is why it would go that way. Yes. So is your question if the coefficient here was a 2? In this case, if the coefficient here was a 2, it would affect this one, and the new answer would then be there's 4 gas molecules on the left and 4 on the right, which means it would then become a no change in that situation. Yeah, so if it happened to be a 2 in that case, it would make it into a no change situation. Other questions? All right, so that's pressure. We're going to talk about temperature here. Temperature works the same as concentration, which means if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards it. What determines whether or not it goes to the right or left is the type of reaction you're dealing with. If you have a exothermic reaction, that means that heat is released, right? And energy is released. It also means that the delta H value should be positive or negative. Should be negative, yeah. And if you have an endothermic reaction, that means heat and energy is absorbed. And that means that delta H value would be a positive number. So when we have an exothermic reaction, we treat the heat and energy as a product, like it's being given off. That means if I increase the temperature in an exothermic reaction, which way should it go? If I increase the temperature, it should go that way to the left, yeah? If I decrease the temperature, throw everything on ice, it should then go towards the product side. Endothermic would be opposite. A plus B goes to C, but heat is considered a reactant in that case. That means in an endothermic reaction, if I increase the temperature, it should go which way? It would be like adding more reactants, which means it should shift away from it and head towards the product side. And if I throw everything on ice and decrease the temperature, it'd be like removing reactants, which means it should head towards it in that case. So for temperature, works the exact same way as concentration. If you increase it, it will shift away. If you decrease it, it will go towards it. And basically, you need to determine, is it exothermic or endothermic as to which way that would mean. Any questions on that one there? Lastly, in terms of change, a catalyst will basically cause no change to occur. Remember, a catalyst will speed up the reaction. It'll just get there quicker, but it will cause no change to occur. The other things, some things that could cause a no change is if you add like a noble gas. They are chemically inert. They don't react with things. So that would also cause a sort of no change situation. And as you were just asked in that question, you could end up with the same number of gas molecules on each side, and that also could cause a no change sort of situation to occur. Question on Le Chatelier's principle there. Okay, we'll lay it up there for today.